Hi, Physics 151. Actually, here we are in room 127. I'm the only person in the lab today. I'm all by myself, so I get to take off my mask. I'm your practicals coordinator. This is normally where you'd be doing your practicals and actually running some experiments. So today, what I thought I would do is just take some videos of me doing some experiments, and then you can analyze these videos and try to measure things like the acceleration, the velocity of the objects, and try to understand a little bit about motion that does not have constant acceleration. And in particular, the motion I want to look at today is called simple harmonic motion. Okay, so we'll start with a simple system where there's maybe a wall over here, and then there's a spring, and here we have a mass. And the mass is, maybe it's on a frictionless surface or something, but it's free to move back and forth in the left and right direction. So we'll set up a position x to describe the position of the mass. Positive x to the right, negative x to the left. And what happens is that there's a force from the spring onto the mass, which is called F sub x is negative k, k is the spring constant, times x. And this is what is called a restoring force, because it restores the position of the mass back towards the origin. For example, when x is greater than 0, so the mass is to the right of the origin, then F sub x is going to be less than 0. It's going to be forcing it towards the left. When x is less than 0, so the position is to the left of 0, then the F sub x is positive, so it'll be forcing it to the right. So what this means is that the mass, the force pushes or pulls the mass toward the origin, always toward the origin. That's called a restoring force, x equals 0. So, and we can know it from Newton's second law. Newton's second law, supposed to be a 2 there, just says that A sub x is equal to the force, if it's the net force, divided by the mass. So this is going to be negative k over m times x. Okay. Now I want to introduce a certain notation here, which is notation, to make it a little bit easier to read this. I'm going to set x with a little dot on it is defined as dx by dt, and x with a double dot is d squared x by dt squared. So that'll just shorten stuff a little bit. And what we can do is now this equation, call this equation 1, then becomes, it's x double dot, which is the acceleration, is equal to negative some constant times x, where c is positive constant. Okay, sort of the handwriting there. Okay, so this is a differential equation, and the way you solve that is you get a trial solution. So the trial solution is that x is equal to a times the cosine of omega t plus phi naught, where I've introduced 3 constants there. Let's move over here. A, omega, and phi naught are constants. So the method for solving this equation down here is you introduce a trial solution. And then what you do is you try it. To see if it works. Let's try it. So you can take the derivative of cosine as negative sine, and you have to use the right derivative rules, x dot is going to be equal to negative a, omega will come out, times sine of omega t plus phi naught. And x double dot, again, just the time derivative of this, there's going to be derivative of sine is positive cos, so this negative stays. You get negative a, another omega comes out, so you get omega squared, and now you've got cosine of omega t plus phi naught. And lo and behold, what this is that x double dot is equal to negative omega squared times x. So what this means is that if your constant is equal to omega squared, and it's positive because that's squared, so that's good, as long as omega is real, then we have solved it. And that's how you do it. And the names for these things are A is called the amplitude of the motion. And the SI units for amplitude are meters. Omega is what's called the angular frequency. It's not the frequency in hertz. This is the angular frequency, which is the same thing, but it's measured in radians per second. Where there's 2 pi radians, means 1 full complete cycle. And then this phi sub 0 is what's called the phase constant. And the units for the phase constant is just radians. And now you know everything there is to know about simple harmonic motion. Okay, so now that you've learned a bit about how simple harmonic motion works, I'm going to show you the setup for the videos you're going to analyze. And there's 2 basic situations. We're going to have a hanging mass on a spring, and we're going to have a pendulum. So the hanging mass and a spring, I've just got 2 masses here. They're both 2 springs and 2 masses. They're both 100 grams. And I hang it on. It goes down to about here. This is a stiffer spring than this one. It's a different kind of spring. So it's the same mass in both cases, but this one hangs a lot farther down. And this is just a portion of a meter stick. You can see 10, 20, 30, 40, 50 centimeters. And what I'll do in both cases is once they come to rest, is I'll pull it down and then release it. Pull it down and then release it. And you're going to investigate how that motion looks. The other system, which I've got over here, is a pendulum. So this is actually showing horizontal simple harmonic motion. And so I've set up a horizontal meter stick here, 30, 40, 50 centimeters. If I pull it a little towards to the right, I'm going to let it go. And it'll swing back and forth. The other thing I can do with this one is that I can adjust the distance of this mass from the pivot point up here. So this is a pivot point. This is a fairly low mass plastic rod that it's attached to, and it looks like about 100 gram or 50 gram mass on there. So I pull it to the side and might change its motion when you take it closer to or farther away from the pivot.